Welcome to AP Calculus AB Lesson 2.3 at finding the derivative of polynomial type, sine and cosine functions. Before we get started, I'd just like to thank Mark Sparks once more for providing this curriculum. So the first part of our lesson here today is finding the derivative of our polynomial functions. And this is going to be really the foundation for about a half to two-thirds of our AP Calculus course, the very basic concept of the derivative. And in our previous two lessons, we've looked at how we define the derivative and how we can find the derivative the long way around. So we really understand where is this coming from. It's based on taking the limit. But what we'll find is that we can actually take a little bit of a shortcut. Instead of having the very long and involved processes, what used to take us several minutes to work one problem, we'll now be able to do the very basic types of problems just through visual inspection. In order to get there, though, we're going to look at this a little bit conceptually one more time and start here with the function f of x equals 3. And this would be, if this is my function right here, 1, 2, 3, and this is my f of x equals 3. For any x value, y is always 3. Here's what my graph looks like. If I were to draw a line tangent to this function, what would that slope look like? Well, if I were to draw a line tangent, meaning touching, but as equally as possible from any given point, I find that my tangent line would actually lie essentially right on my function. And what would the slope of this line be? Well, the slope of any tangent line drawn to, and this function right here is 3, that's a constant, the graph of any constant. Any constant function would be 0. Okay? And we can see then, looking at this a little analytically instead of verbally, if my function equals c, some constant, then the derivative, remember we're learning this notation right here is read the derivative of the function f would equal 0 for a constant. Now, that's going to help explain the one part as we move into this next section here. That might otherwise be a little bit strange, because wherever I have a constant, the derivative of that will be 0, and I'm not going to write plus 0, so we'll just leave that alone. What we're going to do for these here is I'm going to write in the derivative of each function. Then you're going to look at those and try to determine what pattern am I using? What is the algorithm that we're using in order to find the derivative? What is the shortcut? You really want this shortcut. It's worth it. So here are my derivatives. My first function is 3x squared minus 2x plus 3. My first derivative of that function is 6x minus 2. My second function is negative 5x cubed plus 2x squared minus 3x plus 1. And my second derivative, well, the second derivative that I'm finding here, the derivative of my second function is negative 15x squared plus 4x minus 3. Here my function is 6 minus 3x squared plus 6x to the 4th. Keep in mind the 6 here, that's another constant. The derivative of this function is negative 9x squared plus 24x cubed. 3 more. Before we move on to those, we're getting some negative exponents and fractional exponents. Look back at these first 3. Take a moment and study them. Can you tell what the pattern is? How do I get 15x squared, negative 15x squared, from negative 5x cubed? How do I get 4x from 2x squared. How could you describe this verbally? If you have a guess, go ahead and write it in the side here, and then you can check it at the end. Moving on to our next three functions, the derivative of this function is 2x to the negative 2 minus 6x to the negative 3. This function, the derivative is 4x to the negative 1/3 minus 8x to the negative 3. And my last function, the derivative is positive 3x to the negative 3/2 plus 3/2 x to the negative 1/2. How would you describe this in words? I'm not going to write this out in words for you. You can do that by identifying the pattern here, but I can show you the analytical pattern here. And this is called our power rule for differentiation, the power rule. And that's a hint, we're dealing with the powers. The powers are very important. This notation right here, d dx, says if I take the derivative of. I'm taking the derivative of specifically with respect to x. So we use this for now just when we're working with functions written in terms of x. So the derivative of any x to any power, n is my power here, is equal to n, what that power was, times x to the n reduced by 1. And this d dx, this is called a differential operation. A differential operation. Alright, let's take a look at the next page. Now we call this the power rule for differentiation. That's our power rule again. We're dealing with bringing down the power. But in order to use this, first we need to rewrite our function in polynomial form. Our polynomial form is any function that is a sum or difference of multiple monomials. A function is in polynomial form. It's in polynomial form if it is a sum or difference of multiple monomial terms, monomial being a single term. Okay, for example, some number of x to 1 power plus some other number of x to some other power plus some other number of x to some other power, and so forth, plus some constant. So in order to apply our power rule, we need to look at each of these functions and see, is it in polynomial form? And if not, we need to change it. And there's two primary ways that we'll find ourselves changing a function into polynomial form. You'll notice with this first function, I have an x in the denominator, and that was not the case in my example up here. So I need to get this x out of the denominator and move it up to the numerator so it looks like our other examples. And recall from Algebra 2 and Pre-Calculus that we can move a term, we can move a factor from the denominator to the numerator or vice versa and change the sign of its exponent. So I would start by rewriting this. We're still just writing the function. This becomes 2x to the negative 2 minus 4x cubed. Now I'm in polynomial form. We can take the derivative, f prime of x equals 2 times negative 2 is negative 4. Negative 2 reduced by 1 is negative 3. 3 times negative 4 is negative 12. X to the 3 reduced by 1 is 2. And I've now found my derivative, which is the equation that defines the slope of the line tangent to my original function. Remember, whenever we think derivative, tangent line, slope of the tangent line, slope of the tangent line, derivative. In the second question, we see a second major way that we may need to rewrite a function in order to move it into polynomial form, and that is separating a fraction into its component parts. As you'll recall from algebra, you may have seen something like 2 over 3 plus 1 over 3, and you would add those together and make that 2 plus 1 over 3. And then you eventually simplify that and so forth. This is basic arithmetic. In algebra, we might have done something like a over 3 plus b over 3 equals a plus b over 3. But that also means that if I'm given a plus b over 3, that I can separate that by taking each term in the numerator and placing it over the denominator. And I do that separately for each numerator term. All I'm doing is pulling this fraction back apart from where it would have been before I combined over the common denominator. So in this example, f of x, I'm going to take each of these numerator terms and write it over the denominator. Negative 3x squared over x. And these ones, negative 2x over x. And this is now my function. Still the original function, all I'm doing is rewriting it in polynomial form. I can reduce each of these terms, and I get 3x cubed minus 3x minus 2. And then I can take the derivative. F prime equals 3 times 3 is 9. X, 3 reduced by 1 is 2. Minus 3 times 1 is 3. 1 reduced by 1 is 0. X to the 0 is 1, and that basically goes away. And then remember the derivative of any constant. This is a constant right here. The derivative of any constant is 0. So this is my derivative function. Moving on to our third question, we see one more way we need to rewrite a function into polynomial form, and that is expanding parentheses. This is now not purely a sum and difference of terms. It is multiplying. So I'm multiplying terms. That means I'm not in polynomial form. In order to get this into polynomial form, we're going to have to do a little bit of old-fashioned algebra. We're going to start by multiplying these two terms together. And that's going to be a bit of FOIL here. X squared plus 2x plus 3x plus 6. That's these two give me all of this, and then that's still multiplied times 2x plus 1. And that's my function here. And we can go ahead and combine these two like terms, 2x and 3x, into 5x. Right? Now I need to distribute these two across my trinomial here now. 2x times x squared is 2x cubed. 2x times 5x is 10x squared. 2x times 6 is 12x. And then I do the same thing with the 1. 1 times x squared is x squared. 1 times 5x is 5x. And 1 times 6 is 6. This is my function f of x. Combine some like terms again. X cubed I only have one of. I have x squared here and here for 11x squared. I have x's here and here for 17x. and only the plus 6 to finish out my polynomial f of x. All I've done to this point is rewrite this in polynomial form. That's really the most time-consuming part, is keeping all of our algebra straight. Now we can take the derivative. My derivative, running out of space here a little bit, f prime of x, my derivative, equals 2 times 3 is 6, x, 3 reduced by 1 is 2, plus 2 times 11 is 22, x, 2 reduced by 1 is 1, plus 17 times 1 is 17, x to the 1 reduced by 1 is x to the 0, which equals 1. I don't need to write that, but we'll remember that when we take the derivative of x, it goes away, it becomes 1. And then the derivative of my constant 6 is 0, so I don't need to write that. And this is my derivative. Let's see a slightly more straightforward example. F of x equals x cubed minus 5x squared over x to the 5th. We're going back to that pulling apart the fraction concept that we had here. So I'm going to rewrite this. F of x equals x cubed over x to the 5th minus 5x squared over x to the 5th. I can reduce these functions. Now, normally, if we were reducing this in algebra, we would reduce each of these by x cubed and get 1 over x squared, because usually we want positive exponents. In this case, however, it's not that we want positive exponents necessarily, it's that we want polynomial form, so we want our variables to stay in the numerator. We want our variable to be in the numerator. So I'm going to go ahead and subtract 5 from each exponent, divide out x to the 5th, which will give me x to the negative 2nd over x to the 0, which is 1, minus, same thing here, I'm going to subtract out the exponent 5 as we divide by x to the 5th. I get minus 5x to the negative 3. Now we're in polynomial form, and we can take the derivative. The derivative of this function equals negative 2 times 1, x, negative 2 reduced by 1 is negative 3. Negative 3 times negative 5 is positive 15, x reduced by 1 is to the negative 4. And we have our derivative. For this function, the approach that we want to take is to rewrite this portion of our function as x with a rational exponent, meaning it's going to be fractional since we have this radical here. And because it's in the denominator, in order to move it to the numerator, we're going to have to make the exponent negative. So we can kind of see how we do that here. F of x equals 3x. And we'll do this step by step. I'm going to start by rewriting this with a fractional exponent. X, what the power that x is being raised to is going to be in the numerator. And the index of the radical will be in the denominator. So you can see where each of those parts come from here. Okay. Now I want to write this with x only in the numerator, which means I want to get rid of this one. I'm going to divide the top and bottom by x to the 2/3. Dividing is subtracting the exponents, which gives me 3x to the 1/3. This is now my function, and I can take the derivative. The derivative equals 1/3 times 3 is 1, x to the negative 2/3. Now if we go back to the instructions at the top of this page, we were told to leave our answers with no negative or rational. That's here we're referring to fractional. Technically whole numbers are also rational, but it's the fractional we have a problem with. No negative exponents, no fractional exponents, and as a single rational function. Now I missed this when we worked this problem right here, we had negative exponents, and so we should have moved those x's to the denominator and combined over a single denominator. We'll go ahead and do that real quick. This would then equal negative 2 over x cubed plus 15 over x to the 4th. I want to combine these over a common denominator, so this term needs to be multiplied times x in the numerator and denominator. That would give me negative 2x plus 15 all over x to the 4th. And that would be my final answer. Ultimately, it's important if you're working a multiple choice question, which is where you would see a problem like this, that you are able to continue to manipulate your answer until you get one that matches the multiple choice options. In the case of the problem we just worked, I have a negative and a fractional exponent. Just like we started with a radical and changed that to a fractional exponent and then moved that into the numerator, we're going to do it in the opposite direction and start by moving this into the denominator to get rid of the negative exponent. So my derivative equals 1 over x to the 2/3. And then I'm going to change that into radical form because it asked me not to have rational exponents. So I have my x, the 2 in the numerator remains on the x, and the 3 in the denominator becomes the index. And this is my answer. Looking at our final practice problem here, these are little fractions. These are in polynomial form. I have one term, x exponent, and another term, x exponent. So we can go ahead and take the derivative. So 3/4 times negative 4. My 4's cancel, and I have negative 3x to the 3/4 reduced by 1 is negative 1/4, plus 2 times 1/4 is 1/2. X to the 1/4 reduced by 1 is negative 3/4. Now, this is my derivative, but I have negative exponents and I have rational exponents, so we're going to fix the negative first. My derivative equals negative 3 over, and I move the x to the denominator in order to make my exponent positive. And this, the 1 is in the numerator, the 2 is in the denominator, and I move the x down there as well to the 3/4 now positive. Before we change this into radical form, we want to go ahead and combine it into one term. We were asked to provide our answer in a single term when it's a fraction. So in order to have a common denominator, what's missing here is that obviously this needs to have a 2 on it in order to match that 2. And I have x to the 1/4 and x to the 3/4. I need an additional x to the 2/4 so that that'll multiply to make 3/4 here. So this is also x to the 2/4. So this gives me negative 6 x to the 1/2 reduced plus 1 over 2 x to the 3/4 as my derivative. And now I can rewrite my fractional exponents as radicals. Negative 6x, the numerator of 1 stays. I don't need to write it. It's understood. The denominator becomes my index, which is 2, which for a root is also understood, plus 1 over 2 radical x. The numerator remains with the x. The denominator becomes the index of 4. And this is my final answer. Finally, for this half of the lesson, we're going to derive the derivative of the sine and cosine functions. Their derivatives are actually really simple, and you won't be required on the AP exam to do the derivation, but it's important to understand where it comes from. And in order to find this derivation, in order to find this derivative, we need to use two trig identities from precalculus. The first is the cosine of a plus b, which, as you may remember, is the cosine of a times the cosine of b minus the sine of a times the sine of b. And secondly, the sine of a plus b is sine a cosine b plus cosine a sine b. So we're going to use this derivative definition, f of x plus h minus f of x all over h, limit as h approaches 0, to find the derivative for sine and to find the derivative for cosine. And we will start with sine. So I start with my limit as h approaches 0 of my function is sine, so sine x plus h minus sine x all over h. Then using my sine rule up here, I can expand this right here. Still have the limit as h approaches 0. And my sine x plus h is now sine x cosine h plus cosine x sine h minus this original sine x all over h. Now we're going to do a little bit of rearranging because our approach here is that we want to factor out our sine. And we'll see why in a little bit. We're going to factor out sine, so we're going to rearrange this. The limit as h approaches 0 of sine x cosine h. That's all one term. I can't move it around. But I'm going to move this sine over here, minus sine x plus cosine x sine h. A little commutative property of addition here, all over h. And this allows me to factor this common sine out. The limit as h approaches 0 of sine x parentheses cosine h minus 1 plus cosine x sine h all over h. Now we're going to rewrite these as two separate fractions, separate them. Limit as h approaches 0 of sine x cosine h minus 1 all over h. So taking this half here. And then we're going to do this half here. Plus the limit as h approaches 0 of cosine x sine h over h. And what we'll see now is that we've set ourselves up with our limit. Remember, our limit as x approaches 0 are special trig limits. Cosine h minus 1 over h equals 0. And the limit of sine h over h as h approaches 0 is 1. Which leaves me cosine x. In short, the derivative of sine is cosine. Let's see something similar for the derivative of cosine. I start with the limit as h approaches 0 of cosine, my function, x plus h minus the original function, all over h. We're going to use our cosine rule here. Limit as h approaches 0 of cosine x cosine h minus sine x sine h. That's the expansion of this. Then we can tack on the rest, bring down our minus cosine x, everything over h. Again, we're going to rearrange in order to factor out and get that cosine minus 1 format. So we're going to bring our cosine up here. Limit as h approaches 0 of cosine x cosine h minus cosine x minus sine x sine h all over h. I can factor that common cosine out, cosine x out. Limit as h approaches 0 of cosine x times cosine h minus 1 minus sine x sine h all over h. Here's the cosine I factored out. And now I have the ability to split this into two separate limits. The limit as h approaches 0 of cosine x times cosine h minus 1 over h minus the limit as h approaches 0 of sine x sine h over h. Cosine h minus 1 over h, the limit as h approaches 0 is 0. So I end up with cosine x times 0 minus the limit as h approaches 0 of sine h over h is 1, which gives me sine x times 1. Simplifying these, I get negative sine x. So the derivative of sine is cosine. d dx, the derivative of sine x equals cosine x. And the derivative of cosine x equals negative sine x. You can fill that in down here. Derivative of sine is cosine x, and the derivative of cosine is negative sine x.